In the end of the pencil, I have a pin. How many heads does it have?
Well, it only has one head.
Yeah. Now I'd like you to look at the same pin head. This time, look at it underneath the surface of the water, because I'm going to put the pin head into the water. Now how many do you see?
Oh, there's two. Oh, that's neat. It's like a mirror image down there.
Yes. In fact, that's exactly what it is. On the undersurface of every layer of water, there's a mirror. In fact, here, I've rigged it up so it's a little easier for you to see. Now you can look in the mirror here, and up there at the undersurface of the water, and when I put the pin in, how many heads do you see?
Oh, there's two heads now.
Yeah, one at each end, right?
Yeah.
Well, now you said that there was looked like a mirror, and that's exactly what it is, and it's the principle of a light pipe. Have you ever heard of a light pipe?
No, I haven't.
Yeah. Well, that's a sort of relatively new development in science in which they can pipe light around to any place where they want it, and it's based on the idea that a surface of water has a mirror in it.
I see.
Now, let's put it first into a column.
Column?
A column of water, yes.
How do you do that, though?
Come on over here at the sink, I'll show you. See, over here, Michael, is a little light bulb.
What do you need the light bulb for?
Well, I'm going to put it underwater. This is a 12-volt bulb running with batteries, so you can put it underwater without danger of being electrocuted. Okay, I'll put it down here like this and sort of line it up so that I can pour water in here, but here is a little spout. See the water coming out there?
Oh, so you mean like when the water comes out, that's going to be a little column of water.
That's a little column of water.
Oh,
but we have the light underneath the surface. So the light's going to bounce around inside the water, including on that mirror underneath the top surface, and also then be funneled out here. So it'll bounce around inside that column. So I'm going to pour, I'll turn the light on, you pour,
Okay.
I'll pour water, and you hold your hand out like that. First comes water. Okay, now I'll turn on the light. Put your hand down there.
Oh, neat. Light shining on the palm of my hand.
Yeah.
Oh, is that ever neat?
Now I'll disconnect the ones and see if you can see the difference. See it go out?
Uh-huh.
Okay, now see it come on?
Uh-huh.
Okay. So, here, now you can wipe your hand off. Just let that run. In fact, here, I'll put the pitcher down here. So. Now we did it with a column of water. Now we could also do it with a column of plastic. A plastic has some of those same characteristics.
Oh.
Come on over here, I'll show you. Here, let me move this out of the way, because now we can do the same sort of thing with a column of plastic.
That looks like the water running out.
Right, the water, sort of a sharper bend than the water takes. But now that same internal reflection, total internal reflection, is going to happen with a piece of plastic. See it?
Oh, it's coming out the end.
Yeah. I'll turn it on and off, see it?
It's neat.
So the light is bouncing around, hitting the mirror on the inside surface of this. Then here's one that's a little more dramatic.
Now that even bends more.
Yeah,
oh, it
bends
still
all
comes
over
out
the
too.
place. And still, in fact, sometimes I think we might lose it a little bit because this is a piece of square plastic. But haven't you ever seen signs that are on people's desks? There's a piece of plastic that comes up and their name is engraved on it, and light comes up and hits it and it glows.
Oh, yeah.
See, the
I've
light's
seen
going
some of
right through
those
the plastic
before.
like that because it's bouncing off the mirror on the inside. Well, that's sort of the fun things about it, but scientists use it in much more important ways. Inside this tube are little tiny tubes of that plastic. So that means it's flexible.
Yeah, it's bendable.
So if you can get a good source of light over here, but you want the light to be down there, look.
It's coming out.
See, it's coming out down here. So you could put it in a microscope or in a projector, or all kinds of scientific instruments. In fact, they even have one that they put down inside people.
What for?
Well, so they can examine inside.
Oh, I see.
In the throat or in the lungs and in the stomach. And they can also put another tube in there and take pictures, so they need light down there. So the idea of a light pipe is a relatively new development in science that's very important. Then people got the idea that, gee, if you could pipe light like that, here are those little tubes that are inside here, but this time they're together only at this end.
Oh, I've seen one of those before.
Yeah, so here they are at this end all together, but here they are at that end all separated. Here,
wow.
would you hold that? I want to turn off the lights, Michael. Now, why do you see
neat.
little stars like that all over the place?
Because the light's traveling through the tubes.
Right, through those little tubes. The inside surface, called total internal reflection. Jason, here's a nice simple trick you can play on your friends. Just get a piece of stiff paper, cut it like this, and then bend down the edges to form sort of a little bridge.
Okay.
And then you say, I challenge you to blow under there and flip it over. You go ahead, try it.
What? It kind of sucks down like a string is pulling it down or something.
Now, the reason for that is whenever you speed up air, make it go faster than normal air, it can't push as hard at right angles. So when you blow under here, you speed the air up under here, right?
Yeah.
If the pressure is lowered under here, what's going to happen to the pressure over there?
Oh, well, if the pressure here is higher, it'll push down on there. And if they're not equal, it'll push it right down.
Okay, in fact, try blowing again, first gently, and then harder and harder and harder, and you watch it goes more and more down. Yeah, see?
Yeah.
Now, if you turn the card over like this, and you were blowing across like this, where would the greater pressure be?
Oh, well, if there's less pressure up here and the pressure is higher here, it'll kind of lift it.
Yeah, you're pushing up like this. And that's the principle of the airplane wing. Doesn't that look something like an airplane wing?
Yes, it does.
Cross section. Take the pencil and put it in here,
Okay.
and blow right over that area.
Okay.
See it go up?
It lifted, yeah.
Well, designers, when they're designing the airplane wing, they make it that way purposely so that as the airplane is moving through the air goes over the top of the wing faster than it does below. So where is the greater pressure?
Right here.
Yeah,
It
that's what
lifts it.
holds the airplane up. Now, when you try this trick on your friends, you have them try to do it like this. But when you go to do it, you put it about over there. And then blow right about here on the desk with a puff of air. Watch.
Flipped over. Why?
Yeah, why should that be? Well, when you're here, you're making the air go faster underneath here. But if you move it down about like that, and you blow here, as the air goes down here, it's going to slow up, right?
Oh, yeah.
And then it'll start swirling like this. So if you do just the right way, with a little puff of air, you can get that leading edge right here with that upward moving air and flip it over. So try it again. See, just a puff. One more. There you go. This is an egg from a female sea urchin covered with sperm from a male. Scientists use the sea urchin to study the process of fertilization because the female releases her eggs into the water where they're fertilized by sperm from the male. As in human fertilization, of the thousands of sperm that reach the egg, only one will actually penetrate the egg to begin the process of cell division that will eventually result in a new child or sea urchin. At the bottom of the aquarium, I have a little nut and bolt.
Yeah.
And I would like you to reach in there and take out the nut and bolt with your hand.
Okay.
Okay, now you notice you got your hand wet.
Yeah, I did.
I would like you to do that again. First of all, wipe your hand off so it's nice and
Okay.
dry. And this time do it without getting your hand wet.
How would I do that?
Well, the reason why your hand got wet is because as you went down through the water, you remember there's a sort of a little invisible skin on top of water called surface tension?
Yeah.
In order for your hand to get wet, you have to break that surface tension as you go down. So all I have to do is prevent you from breaking the surface tension by putting this little powder over the top. This is a powder that is the spore of a moss called Lycopodium. And it's filled with sort of a rosin-like material that doesn't get wet with water.
Oh.
So I now have a nice layer over there. I'll drop the bolt in there.
Okay.
You turn around and see it now?
Yeah.
Okay, I want you to reach your hand in there very slowly, go down at the bottom, pick up the bolt, and bring it out.
Okay. Boy, that's neat. My hand didn't get wet at all.
It's full of a lycopodium powder, but it isn't wet.
Yeah.
Now, why is that? Just so you remember.
Because the Lycopodium covers the surface.
Right, and there's a little skin over there so that, and if you don't break the surface tension, your hand won't get wet. Would you please put the bolt back?
Okay.
Still not wet, right?
Nope.
Okay, very good, thank you.
Thank you.
Here's a question for you. This represents the sun, and this is the orbit of the Earth going around the sun.
Oh.
Now, at one point in its orbit, it's 94 million miles from the sun, and at another point, just 6 months later, it's 91 million miles. Which position is summer and which position is winter?
Well, it seems more logical that if the Earth is close to the sun, like in the 91 million miles, like the sun is hot, so when the Earth is closer, it'll get more heat, so it'll be summer.
Sounds logical, doesn't it?
Yeah.
Well, that's wrong.
It's wrong?
But you're wrong and right at the same time.
How can I be wrong and right at the same time?
Well, I'll show you. I'm going to get the Earth out. You go see that spotlight I have over there?
Yeah.
Go around and pull it over here so that you can shine it on the Earth, and that's going to be the sun. All the way up, that's it. Now bring it over here, and so we can get 1 unit of sunlight like that, okay? Now you know the Earth this is the North Pole, that pin up on the top. The North Pole doesn't point straight up like that. It points away from and toward the sun at various times in the orbit, right?
Yeah, it's tilted at 23 degrees,
23 and a half degrees, okay. Right now, the sun is sort of concentrated in that little spot because the North Pole is tipped toward it. It just so happens that the distance from the Earth to the sun at that point is 94 million miles.
So that's how I was wrong?
That's how you were wrong. Now, what happens 6 months later, the Earth is tilted away from the sun like this.
Oh, I can see that. It's kind of spreading out over a larger area.
So that's why it's cooler. Now, I said you were right and wrong. If this is winter in the northern hemisphere, what's happening in the southern hemisphere?
Well, the light is going to be concentrated as summer in the southern.
Because it's tipped toward the sun in that case. And up here,
It'll
when
be,
it's summer up here?
It'll be spread out in the southern as winter.
Right. So that's a nice sort of question to pose to your friends. When is the Earth closest to the sun in the summer and the winter? And now you know that the Earth is closest to the sun in the winter. Have you ever experimented with paper chromatography?
No, but I have heard of it.
Well, there are samples here on my desk of an important chemical technique in which chemists take chemicals apart based on the fact that liquids move through filters at a certain rate and have various attractions for chemicals. So let's do one. These are food coloring, and I have a bunch of food coloring here. Here's what you do. See how I've cut a tongue in the paper like that? So you cut a tongue from this outside right to the center like that. Okay, now cut off the part of the tongue, about half. Okay, now we want to, here's some Scotch tape. You want to tape that to this dish to keep it from falling in.
Okay.
Okay, put one here. And one here like that. See, now you see it's suspended above the bottom of the plate.
Yeah.
Now we want to get our chemical that we're going to analyze. Here are 4 choices. Take your choice.
Green.
Green. Okay, you know how to put a drop right there at the end of the tongue.
Okay.
Very good. Now, put the top back on again so we don't spill it all over my desk. Now what we have to do is put a solvent. Do you know what a solvent is?
No.
Well, water dissolves sugar and salt, right? Well, various chemicals dissolve the kind of material that's right here. And what we're going to use is plain ordinary rubbing alcohol.
Okay.
Alcohol dissolves different things than water does. So now you put it like that. What's going to happen as the alcohol gradually comes up the tongue?
It's going to spread out?
Yes, it's going to spread out. In fact, see, here's one in which there was red here and blue, and as the alcohol moved away, it carried the chemicals at various rates and deposited them on the filter. Scientists use this, especially important in dealing with proteins, because the proteins are deposited along a filter strip like that. And what you have to do really is cover it like this because you don't want the alcohol to evaporate too fast and move. So it should go as slowly as possible to dissolve it. Then about an hour or so later, if you take that off,
Okay.
here's what it'll look like.
Oh, that's pretty.
Isn't this pretty?
Yeah.
Yes. So a nice technique that you can play with by using copper filters, and it's called paper chromatography. This is part of a plant, and because it's so colorful, you might think it's a flower, but it's not. It's the edge of a leaf. While most leaves are green, some are highly colored. Exactly how the colors are produced and how they help the plant is unknown. A scientific mystery in the colorful leaves of the Coleus. You recognize this, I assume, Michael?
Yeah, it's a kettle with water in it.
Yeah, we're boiling it, right?
Boiling water.
As you can see, the water vapor coming out of here. Well, we're going to make it into a steam engine.
Steam engine?
Have you ever seen a steam engine?
In pictures and movies.
Well, first of all, here is a balloon filled with water, which I will place on the top, like that, okay? Now we have a great big leak there, so we want to plug that up. Here, you
How?
take this, and here's an apple. Just jam the apple on good and tight over the spout.
Okay.
Push. There we go.
Oh,
There's
it's
our
going
steam
up.
engine.
That's a steam engine?
Sure.
It's going up and down.
Okay, why?
Because the air, it can't go through there, so it has to go somewhere, so it's
The air?
pushing. Yeah.
Air?
Well, the steam.
The steam, okay.
It's pushing up and down on that.
Right, and this is the piston of the steam engine. When you change water to steam, it takes up a lot more space. So it tries to expand, and we have the balloon on top. That's the piston in the steam engine. It gets a series of pushes. So I thought you'd like to know we're taking a tea kettle, a piece of apple, and a water-filled balloon to make a steam engine in the kitchen.
It's neat.
Tanis, what's making that propeller go around?
Well, it's obviously the wind.
Well, no, put your hand in front of that round thing over there in front and shade the sun from it.
Okay. Oh, the propeller's slowing down now.
Put it in all the way, cover it all the way.
Okay. Yeah, it's coming to a stop.
Okay, now take your hand away.
Okay. It must be the sun because the propeller is starting up again.
Yes, that's a solar cell.
Yeah,
Have you ever heard of that?
Yeah,
Solar
I've
energy?
seen solar energy houses like that.
Yes, which they have a whole bank of these. Well, the idea of changing the energy of the sun and making it into electricity is a fairly old idea. In fact, watch how I'll stop this for a minute.
Okay.
Have you ever seen one of these? This is an exposure meter.
Yeah, I think I've seen one of those before.
And if I watch what happens with my finger over the top. See how the needle goes down?
Yeah.
And then it goes up?
Oh, yeah.
Well, what this is actually inside here is a little electric meter.
Really?
And the more light that falls on the little cell inside, why the more electricity is generated.
Oh.
And that's the same thing that's happening here with this cell. As light falls on here, electrons are kicked out from each one of those little panels and sent around over here to the back where I have a motor.
Oh, yeah, I see it.
To the other end of the motor is attached the propeller. So now if I let go, the energy of the sun can make the propeller go around.
Yeah, that's neat.
In the future, you'll probably be using solar cells like this, have a whole roof full of them. You may make toast,
yeah.
have fans running, get electricity one day from solar energy via solar cells. Come on over to the sink and fill the bottle full of water. Okay. Now here's a playing card. So I'm going to put over the top like that.
I know what you're going to do.
What do you do?
You're going to turn it over and the water won't fall out.
How'd you know about that?
My science teacher did it with me in grade 4 or 5.
Okay, well, you do it then. Okay. I'll be the science student and you be the science teacher. How come the card doesn't come down? Gee, it's supposed to fall, right? You'd think it would.
But what do you think's happening?
Well, I think that the water starts to fall first, and then because the minute it starts to fall, it lowers the pressure up here, and that means that outside air pressure pushing around on all sides is pushing up on the card, and that's one of the things that holds it up into place. And the other thing is that all around the edge, where you can see how the card is wobbling a little bit, there's a little bead of water, and the water has surface tension, which is sort of like an invisible skin, and that's preventing the air from getting in there to push down on top. Am I right?
Yeah, good. I'll give you an A.
Well, thank you.
What would happen if we used something else besides a card?
Well, I've tried various things. Wax paper is pretty good. You turn it over and I'll get some wax paper. That works reasonably well. But you shouldn't use too big a piece. So I'll get a piece that's just slightly bigger than the mouth. Can I do it this time?
Yeah, go ahead.
Thank you.
Oh, good.
Yeah. So when you try this at home, you can use practically anything as long as it doesn't absorb water too much. I wouldn't try facial tissue or toilet tissue or something like that. A piece of paper might work for a while until it's soaked and took away some of the water. It still might work, but I like something that has a smooth surface like wax paper, or my favorite of all, of course, is the card, because everybody has an old deck of cards around, and that works really best like that. And notice, even though there's some of the water has leaked out, see that little bead of surface tension up there? Yeah! It broke.